system equation. Yep. And then at the very end of lecture, we pointed out something which was a little unfortunate, right? Which is, in order for this system to work, I had to take all of these vertices and explicitly pin them down on a boundary curve. Because if I don't, well, what is like sort of the best, like lowest, the map that brings every vertex as close as possible to every other vertex without any constraints? Yeah, it just puts everything on one point, right? They're all super close to each other when I do that. Yeah. And so the way to understand this linear system is it's kind of like a bunch of rubber bands that I'm pulling stuff out. I pin a few on the outside, and then it's letting everything else relax. But that's putting a lot of work on the artist, right? I mean, the artist has to place all these boundary vertices. And depending on how you do it, actually will lead to different distortion on the inside. Yeah? And there's a weird relationship between those two. So I think the very last question we thought about at the end of the last lecture last time was to say, well, what if my set V naught, like the set of things that I pinned down and then let everything else relax, what if that set is empty, right? Then this problem is invalid, right? It's not going to make a very interesting map into the plane. So does anybody have ideas? You've had a whole few days to think about it. Yeah? Sure, if you had a boundary curve that you care about in the plane, you could make the positions along that curve free variables. There's a little bit of an issue with that particular approach. It actually shows up in one of my recent research papers, which has to do with like if you have a fishnet, yeah, and let's say that I'm trying to wrap a fishnet around a physical object, right? And I'm using my fishnet as sort of a model for a discrete piece of geometry. There's an issue, which is that you can slip through the cracks, right? And so even if I have a parametrization problem, I want to map everything to some boundary curve, right? And all my energy cares about is the lengths of the edges of a bunch of triangles. You can, if you're not careful, you can end up in a scenario where everything kind of slips around the outside and still ends up at a single point. Yeah? But you're absolutely right that is a technique people use. They just have to be a little careful to avoid that case. Any other ideas? Yeah. Yeah, I encourage you to take a look at Sebastian's first research paper in my group, which does precisely that. So this wants everything to be close. You got another term that goes really big when they get too close. These are both great ideas. They're sort of nonlinear things, right? So they incur a lot of extra work algorithmically. What if I wanted to stick with using just numerical linear algebra? We're thinking about. One thing we're going to try and emphasize in this class a bit is just modeling and like how to go from some messy application problem to this notation here, because I think it's a useful skill. And I'm taking a stand. So think about it for a minute. One thing to do is just say, okay, like I don't want all my vertices to end up at the same place. So let's just start baking in constraints into my problem until that can't happen, right? So for instance, one thing I might do is say, okay, well, currently I'm not happy with this problem because I could end up with the solution xi equals 0 for all I. That's not so great. So maybe I add a constraint, which is the sum over all I of the norm of xi squared. There, done, solved. Right? They can't all be 0 if I made their norm sum to 1. Yeah? That's one solution to this problem. Yeah. Does this fix it? It is a quadratic constraint. So it still doesn't fix it, right? This just says, like, I could put everything at the same point, a distance 1 over n away from the origin. Yeah? So I say, well, shoot, that's annoying. So how can I fix that? Yeah.
Sigma xi minus xj times yi minus yj greater than equal to some real number.
It's an interesting idea. Yeah, we'd have to figure out what the y's are and what you mentioned, but a small variation of that absolutely is right, which is to say that if I just sum over I and make them centered at the origin, well, think about what these two constraints do together, right? This guy says that they can't all be 0. This one says they're centered at 0, which means if I have one point here, I need another point over there to cancel them out. Okay, so I have a single quadratic constraint. This thing, if you notice, happens to be in the null space of the operator that happens here. Right? Because if I shift everything by a constant, nothing happened to my problem. Yeah? Anybody have a guess of what this kind of a problem looks like? So in effect, I can kind of write it like this. I'm going to ignore the sum equals 0 constraint for a second. Yeah? Embed the whole mesh without pinning stuff on the boundary.
But make it on the plane.
On the plane. Yep. So your variables xi are in R2.
Is that enough just having that like because it's just like taking the intersection of
It turns out that is enough, actually. We'll see. I'll show you some examples in a second. So actually, I'm noticing now my slide gives away the answer, right? Which is I have a quadratic objective and a single linear constraint. And this is exactly an eigenvalue problem of A transpose A if my matrix over here is A. We're not going to derive this in class. If you guys aren't comfortable with this equivalence here, that's OK. It's something you probably blew past in linear algebra class. But you should get out some scrap paper, do your Lagrange multipliers, and convince yourself that this is true. Does anybody know what where this A transpose A, like where he comes, like when you solve least squares, right, this shows up a lot. And that's because it shows up in a set of equations called the normal equations, right? A transpose AX equals A transpose B. And basically it shows up here for the same reason. Yeah. Okay, right, so it turns out that if I want to solve this optimization problem, this is equivalent to computing the smallest eigenvalue of this matrix A transpose A. Yeah. Of course, we added a second constraint here, but we got particularly lucky in our problem because this corresponds to the vector of all ones in a constraint. It's just saying everything sums to 0. Yeah? And that vector is in the null space of our matrix anyway, right? If I add the vector of all ones to my x's, it doesn't change the objective value. So it turns out I can just kind of ignore it and compute the second biggest eigenvalue of my matrix because the smallest one is what? 0. Yeah? And out comes a nice algorithm for parameterization. And this is actually more or less what's built into most of the parameterization software that you have in like Maya, all these 3D tools. So all they do is solve an eigenvalue problem where the matrix hiding the inside is Laplacian, just like we talked about last time. If you're not used to seeing this matrix here, don't worry about it. We're going to cover it in a ridiculous amount of depth in about 3 weeks. But the main point here is that anytime you see a quadratic objective and one quadratic constraint, that's a solvable problem. It's just an eigenvalue. And that actually this is extremely powerful language. And so essentially, I would say about 85% of what we do in this course is going to boil down to the two problems that we just wrote down. One is just a linear system of equations in disguise by minimizing something quadratic. And the other is an eigenvalue problem, which is a quadratic thing plus one quadratic constraint. Yep. So those are the things to think about. I think I'm going to skip over this example because we're running a little late. There's a nice paper that combines all of these things together, computes eigenfunctions, and then solves a linear system to extract a map from one cat into another. It's kind of a fun read. It was actually one of my first papers as a graduate student. It was fun to work on. So very briefly, I thought we'd mention just the generic case of unconstrained optimization. Several of you are machine learning students. You probably know more about this than I do. When I want you to notice an equation, we'll make it kind of big. Right. So the unconstrained case now is going to say, well, maybe I don't know that my objective is quadratic. Maybe I want to try some of these other interesting ideas for parameterization where I add, like a 1 over x looking term, which is cool, but now I can't solve a linear system. What is a person to do? Does anybody have any ideas? What sorts of algorithms are out there for just solving unconstrained, unstructured minimization? Gradient descent. Fabulous idea. Basically walk downhill. Yeah? We're going to use this mostly as an excuse to remember what the gradient is, right? If I have a function, the gradient is the direction that points where? Up. Thank you. And so minus the gradient points downhill. So the gradient descent algorithm is extremely simple, right? If I want to find my minimizer, I just step a little bit down this guy. Okay? Any other algorithms generically for this kind of a problem we can think of? Random guessing. Physicists really like that. They give it cute names, right? There's like what, particle swarm and annealing and genetic algorithms. These are all basically random guessing. Yeah, I would perhaps avoid those unless I had to use them. But there are cases. But any other algorithms for differentiable functions? It's 2 times differentiable? Newton's method, right? So in Newton's method, what do? I take a second order approximation of my function, I minimize that, and I iterate. Yeah? So anyway, these are mostly just Google search terms for you guys to go back and review and dredge up in case you don't remember. There's all kinds of fun algorithms out there. I think I'm going to skip over talking about these things because really they're not relevant in our discussion for now. But the nice thing is it allows you to do all kinds of crazy geometric algorithms. So here is an example where I want to solve shape interpolation. So for instance, I have this straight bar, and then I have another pose of this bar in this little curled up configuration, and I want to interpolate from one into the other. This is not a linear problem. One easy way to see that is, let's say that I have a 3D model of a human, and I put its arm straight up, and then I have another pose of it where I put its arm straight down. Let's say that I use a linear system of equations to interpolate. What's going to happen halfway in between? Yeah, you're not going to have an arm, right? Because everything moves on a straight line. Yeah? So this is an example where, by virtue of there being elasticity, you really have to account for these weird nonlinearities that happen. And so they have some interesting models there. So for instance, in this case, what they did is they said, I'm going to interpolate the lengths of all of the edges of my triangle mesh as a function of time. And then try to find a 3D embedding of a mesh with those prescribed edge lengths. And similarly with dihedral angles. And unfortunately, things like length and angles and so on are just nonlinear functions, and that's life. So the algorithms that they have to deal with are these generic nonlinear things. Okay, so anyway, hopefully you guys have the basic idea here. I mean, in software, of course, the second you have a gradient, you can throw anything you want into a model like this and pray and cross your fingers. And oftentimes you can get some really interesting result. And in many of your final projects, I'm guessing you'll have to use some of the tools like this. So just to be aware, there's many of them out there. One final point of calculus review, and then I promise we're done, and we're going to move on to differential geometry and curves and surfaces and all that good stuff. And that's Lagrange multipliers. So we're talking about optimization with constraints. Well, we were talking about optimization. Now we're going to talk about optimization and add a constraint. Right? So generically, we talk about minimizing a function f of x such that g of x equals 0. 0 is a reasonable right-hand side here, right? Because I can always subtract whatever I want, put it all on one side. These are extremely important in geometry world because we have many, many boundary value style problems, right? So for instance, if I want the shortest path between 2 points, well, what do? I look over all the sets of paths, and I have this constraint that the 2 endpoints are fixed. Right? And when I do the gradient descent procedure, I need to account for that as I do it. Yeah, in that particular case, there's an easy way to do it, which is just leave those 2 points alone. But in other cases, it's not so easy. Okay. I'm not going to go through derivation of Lagrange multipliers because hopefully we're all grown-ups here and we've seen them before. If this is another term you haven't seen in a long time, that's fine. Just go home and Google it. Come to my office hours. We'll help you out. But I thought really quickly we'd draw kind of my favorite interpretation of how to think about them, just to give you some intuition. Because essentially what we're going to do in this class is no matter what equation we write down, there is shape sitting underneath it. Yeah? And this is a great example where I think when you talk about constrained optimization in calculus class, what do? Well, you say, OK, fine. So I'm going to construct some function. We'll call him, I don't know, lambda of x like that. And it's f of x plus, right? And then you take the gradient of this thing with respect to x. You set it equal to 0. That's your constrained point. Right? This is Lagrange multiplier. But this isn't a terribly geometric thing. This is like a formulaic, kind of boring calculus class thing to do. So let's think about it for a minute. What's actually going on in these kinds of problems? So in particular, let's say that I have a function f of x, and we're going to use level sets to draw it. This is also my excuse to give a different visualization of a function here. So in other words, as these gray values get brighter, they correspond to locations where f of x is getting smaller. Yeah? And so if I just had minimized f of x, I would find this point here. But I'm going to say subject to g of x equals 0, which is this red curve. Yep. So what's going on in Lagrange multipliers? Well, now we have 2 different gradients we have to deal with. Yeah? In particular, there's f and there's g. Yeah? But they're slightly different objects, right? I want to stay on the g equals 0 level set, whereas I want to minimize f. Yeah? And that's really what's going on in this condition here. Okay, so right. So let's say I'm doing gradient descent. Here's the gradient direction for f. There's downhill. Yeah. Here's the gradient direction for g, and what do we notice relative to the constraint manifold here, this red curve? It's perpendicular, right? So in a sense, this direction is actually the direction I can move if I want to make the constraint the least happy. Yeah, I want to break the rules. That's how I do it. Okay. The idea of Lagrange multipliers is, let's say that I have a feasible point like here, And I want to know if I can decrease my objective even more, right? Well, the gradient direction points downhill. And that vector has some component which is orthogonal to the constraint vector, meaning that I can, if I think of there being like a little bead sliding along this piece of string, there's still a direction I can slide that bead which keeps the constraint happy and decreases the objective, right? When's the one time that can happen? Well, it's when I say, in order to walk downhill, I have to violate the constraint. Yeah? And that's this scenario right here, right? So the idea is that to walk downhill, right, the gradient of f, or minus it, wants to point that way. But that's exactly opposite the direction that I'm allowed to walk in order to maintain the constraints. Does that picture make sense? So if I write that down, what do I get? I get that, the gradient of f and the gradient of g are parallel vectors to one another, right? They're at odds. And look at that. That's exactly the Lagrange multiplier condition, right? So anyway, that's the sort of geometric way to think about what's going on when you're doing constrained optimization, is that the only direction I can move to violate my constraints, at least at first order, or rather the only direction I can move to improve my objective function is exactly the one that violates the constraints. Yeah? Any questions about that picture? Fabulous. And of course, there are many different examples here. Here's one nice one. So let's say I wanted to minimize, let's say A is a symmetric positive definite matrix. And I want to minimize x transpose AX subject to this thing. Oh, there should be a -1 here. I'm sorry. The norm of x equals 1. Otherwise, this is an easy problem to solve. Yeah? So let me write it down. So here's the problem. Yeah? By the way, for convenience, obviously that doesn't change the problem, but it does make my arithmetic marginally easier. Yeah? So what does my Lagrange multiplier condition say? It says that the gradient of this is parallel to the gradient of that. Yeah? So if this is a symmetric positive definite matrix, what's its gradient of x transpose AX? 2AX. All right, put the 1/2 here to kill it. Yeah? So I have AX. And it's parallel to the gradient of this thing. What's the gradient of the norm of a vector? 2x. I don't like the 2, so maybe I do that. Yeah? So I get that. And notice this is exactly the equivalence that brings you to eigenvalue problem from optimization. Okay? So anyway, these are just cranks that you should get used to turning again that you probably saw in calculus class you haven't thought about in a long time and are worth a bit of review. So the way that I like to think about this is that roughly Lagrange multipliers are just turning constrained optimization into root finding, right? So this is a system of equations I got to solve. There are all kinds of fun examples. Another good one is this world of polycube maps, which my student Paul really likes, where I want to take a 3D surface and turn it into something whose faces are kind of parallel to the coordinate axes. This is useful in certain computer graphics and meshing tasks. And so the way that they do that is they look at the normal vectors for every face, and they put a norm on it, which is minimized exactly when those vectors are parallel to the plus or minus x, y, and z. This is some crazy nonlinear thing, but they additionally need to throw in constraints to make sure the surface doesn't collapse in on itself. Okay, so finally, we're going to do something that I don't think you've seen in calculus class. You might have seen it in physics class, but certainly not in intro calculus. And that's the idea of taking a variational derivative. And we'll do it here for one problem, and then it's on your homework for a different one, for defining curvature. By the way, several of you have already started, which is great. Glad to see. Okay, and the big idea here is that in geometry, rarely is the quantity that we're trying to compute a number, right? It's typically a shape. Yeah? And so one of the big efforts in the history of differential geometry was to say we have all this interesting and useful machinery from calculus, which applies to functions that take in a number and output another number, or take in a point in Rn and output a number. How can I extend that to problems that take in a shape and output a number? Right? Like, can I find the curve that minimizes length, or the surface that minimizes surface area, or what have you? Right? Anybody know what that's called? The surface that minimizes surface area given a constrained boundary? Minimal surface, right? Good example is the soap bubble. If you're a differential geometry professor in the math department, you're like contractually obligated to bring in an awkward tank of bubble liquid and wave around a wand, and it never works in class. Okay, so the basic idea of variational calculus is basically a sneaky trick to extend calculus to the case where your unknown is an object that isn't just a point. And the basic way that we do that is based on some intuition here. So let's say that I have a function f, and he goes from Rn to R, and I want to minimize it, right? And let's say that in particular, I have a point x star, and he is some local minimizer of my problem. Okay? So what's the typical way to check this? Well, I take the gradient of f, I evaluate it at x star, I get 0, and life is good. But this picture isn't going to extend particularly well to the case where this is like a curve and not a number. Yep. So instead, we use a slightly different intuition, which is now let's take a vector v in Rn. So just some arbitrary vector v. I'm going to define a new function phi. And he's f of x star plus hv. Okay? So, if we think of Rn as some coordinate axis, here's my x star, right? There's some vector v. Then essentially what have I done? I've just taken a slice of my function through that line. And now, of course, I could plot this thing, right? So here's h, here's phi of h. And if x is a minimum of this multidimensional function f, what shape do I expect to have for this plot? What should happen at h equals 0? Should be a local minimizer, right? Because what did I do? I took a pair of scissors through space, right? So maybe I have a bunch of level sets like that, right? Now I chose a point, I chose a direction, and I looked at just the slice of my function through that point. And so when I make that 1D plot, it had better be minimized at that point, or else I have evidence that I wasn't at a local min. Yeah? Everybody with me so far, the reasoning? Cool. Did this have anything to do with my choice of v? No, this is true for all v. Yeah? Okay, so here's the kind of sneaky trick in variational calculus, is that this picture of what it means to be a local minimizer, where like no matter what direction I point my toes, if I start walking, the function increases, that picture extends nicely to the functional case. Even though taking the gradient, well, we got to figure out what it means to take a gradient when your input isn't a point. Yeah? Does that high level kind of story make sense? So let's carry it through. And this is going to be also a great excuse to review one more piece of calculus we're going to need in this class, which is integration by parts, or Stokes' theorem, or Green's theorem, or divergence theorem, whatever we want to call it. Yeah? They're all basically the same. Okay, and that's going to lead to this idea of something called the Gateau derivative. Just out of curiosity, how many of you have seen this before? It's okay if you haven't. We have officially started what I am considering new material in this course. Okay, so the idea of the Gateau derivative is kind of like defining this function phi, and then taking the derivative with respect to h and setting it equal to 0. Right? So this is a necessary but not sufficient condition to be a local minimizer. Right? So see, look what I did. So here I took like a slice in the phi direction along the h. And this thing should be 0 if I evaluate it at h equals 0, and I'm at a local min. Okay, so that's the basic story we're going to fill in here. And the great thing is that that's going to work not only when u and phi are points in Rn, but also when they're functions. Really sneaky trick. I love this stuff. Okay, so I thought just for fun we would do one variational calculus problem in class, and then I will let you guys go home and struggle with it on your homework a little bit. It's what kind of thing, you only have to do it once, and then it's not so hard. But the first time it's painful. Okay, and so to do that, I thought we would write down this optimization problem on the board here and show that it corresponds to a partial differential equation. If you've heard of the Poisson equation, we'll see that it has a nice explanation in this language here. Any questions so far? I know I speak too quickly and I get enthusiastic and excited when variational derivatives come up. Okay. So I think we'll do the first one on the board, and then on Piazza you guys can think about the second one. The second one's a little tricky because there's also a constraint in there, so you'll have to think about how to adapt Lagrange multiplier to this case. Okay. Right, so here's the basic optimization problem that we're going to solve in this blue square up here. The idea is that as input data, I'm given some vector field v, Notice V is bolded here, right? So there's like, I'm sitting, R2 is good enough. I'm sitting on the plane. I've got vectors every which way. And I'm sitting in some region omega, like that. And I suspect that there exists a function f whose gradient looks like my vector field. That's the problem I'm trying to solve, right? So what I want to see is whether I can find a function f which goes from my region omega into the real numbers such that the gradient of f equals or is maybe approximately equal to my vector field v at every point on the plane, or at least at every point inside omega. The basic setup of my problem makes sense. So I'm given as input a vector field v. I'm trying to find a potential f that kind of explains it as its gradient. First of all, do I expect there to always exist a function f with an equal sign here? No, right? So think about a vector field that circulates, like in a circle, right? Remember that gradients point downstairs? Yeah, so it wouldn't really make sense to have a gradient vector field point in a circle because you'd be spiraling downward, but it met up on itself. So one thing we can do is set up basically a least squares problem, right? That says I want to find the function f that minimizes the square difference between the gradient of f and my vector field v integrated over the whole domain. That's a pretty typical thing to do. Okay, and we're going to see that a lot of differential geometry problems can be written this way. Like we're going to talk about mean curvature in a few lectures, and we'll see that here, if we look at the direction that decreases surface area, we'll get the mean curvature direction. Okay. So, cool with the setup? All right, fabulous. So let's try and make this look like a calculus problem. You know, we got one hammer. Let's see if we can hit some nails. Okay? So in particular, squinting my eyes a little bit, if I want to minimize something subject to something, maybe what I do is I define an energy which takes in a function f and gives me back the integral over omega of gives back my objective function. Okay? Is everybody going to be cool if I stop writing these vector hats? I get tired of it. I'm going to forget anyway. Okay. Fabulous. So let's go back to that variational picture that I showed you before. And in particular, let's just invent another function. By the way, just in general, when you have a square, life is a little better if you put a 1/2 here. Obviously, this doesn't affect your problem. Okay. So let's say that you take some other function g. By the way, in this class, we're not going to worry about things being like what level of differentiability and all that stuff, which you really should be careful about. So we're going to use the phrase sufficiently differentiable quite a bit. And this is one of these cases. We will take g to be sufficiently differentiable. Okay? And now I'm going to define a new functional. And we're going to call him, I'll call him phi sub g. And I'll just say he's equal to e of f plus hg. What is the input to phi? Like what world does that thing live in? It's just a number. Okay, so h is just a number and it's like a scale in front of this function g. That makes sense? Okay, so this thing takes in a number h, constructs this crazy function f plus hg, evaluates the integral, and what does it output at the end of the day? Another number, yeah? So, right, so this thing goes from the real numbers into the real number. Sneaky, huh? I didn't know how to do a problem where finding a function g. Functions are hard unknowns to work with. But hey, I know how to take derivative with respect to one number. So let's just see how far we can get with that. Yeah? So let's say, suppose that f minimizes my energy functional E, right? Then in particular, what does that tell me about d over dh of phi sub g of h evaluated at h equals 0? First of all, let's parse this expression here. What is this saying? This is like differentiate in the input to this function here, and then plug in h equals 0. What should this value be if f is a local minimizer of my energy? 0. Do you see that? Because what I did is I said, okay, well, if f is a local minimizer, well, what happens if I perturb f by any function g? Well, my objective gets worse, right? Because f is a local minimizer. Yeah? So if I define this crazy function phi, I mean, in some sense, this is a weird black box, but it's some black box with a derivative. We're used to that in deep learning. Yeah? Then fine. Then if I differentiate this thing, then certainly a necessary condition is that when I differentiate it, I get 0. Here's the crazy thing that happened. Does this argument depend on g? No, this is true for all g. And this is going to be our way to minimize this function. Everybody get the sneaky trick that I did? I turned this into a one variable problem. Okay, so now let's do a little bit of arithmetic. And this is where I'm going to start making mistakes, so get excited. Okay. So let's take the derivative of phi g. So phi g prime of h, that's equal to d over dh of the integral over omega v minus, I should be careful, v of x minus gradient f at x dx. Everybody with me so far? All I did was put a d over dh in front of everything. Here's the thing. This integral is over x. It isn't over h. So, right, so if I differentiate, oh, wait, there is a mistake here, right? Because this should be f plus hg, right? So this should be minus h grad g of x, also inside of that norm. My apologies. Now does everybody agree? You shouldn't, because like I make a lot of mistakes. You haven't, in case you haven't caught on. Okay. Otherwise, the derivative would have been 0. So it's good to sanity check. Okay. So this integral is over x. Yeah. It's not over h. So one thing that I can do is differentiate under the integral sign. I mean, I can exchange these two guys, and that's perfectly fine. It's kind of like the derivative of a sum is the sum of the derivatives, right? It's exactly the same fact. So let's do that. So I'm going to be the tiniest bit sloppy because I don't feel like rewriting everything. Cool. That's differentiating under the integral sign. Everybody should go home and prove that theorem. It's like one of those things that like somehow feels true, but like requires proof. Yeah. Okay. Right. So what is the derivative of this thing? All right. And I forgot a 1/2. You guys aren't catching me on anything. Okay. So what is the derivative of this guy? Well, remember that this is really just the dot product of this vector with itself. Yeah. So by the product rule, yeah, what do I get? So this is equal to the integral over omega of v of x minus grad f of x minus h grad g of x dot product with the derivative of this thing with respect to h, just grad g. Cool? Did I? Did I?
Yeah.
I did. Yeah. Okay. Thanks, Sebastian. Okay. All right, so everybody agrees this is the derivative with respect to h? Well, I managed to lose you all yet because I'm trying. Okay, so right, so if we want to kind of follow the outline here, what else do I need to do? I need to plug in h equals 0, right? Because that's the only place that I care about. Yeah. So when I do that, what do I get? I get phi g prime of 0, and this thing is equal to the integral over omega. Now this thing goes away, right? So I have v of x minus grad f x dot product with grad g of x dx. The irony is all these mistakes are on my scrap paper as well. Yeah? Okay. Everybody with me so far? Here's the thing. This thing equals 0 for all suitably differentiable functions g. Yeah? What was that? No? There's high likelihood of a mistake. It wouldn't be the first time. Obviously, by proof by example. I'm going to flip this screen up. I'm listening.
Wait, what's the minus sign from?
Man. What's the... Yeah, so there's a minus in front of the h. Yeah. I want to turn this projector off, but I'm not clear which of these is going to do it. So I hit that one, which said left. I'll just write on the board. Okay. So in particular, let's say that I have, well, how much detail do I want to do this? I want to do it in detail. Okay. Whenever you see an integral over a region and there's a dot product and a gradient, this thing should be like screaming out at you to do something. Integrate by parts, right? Anytime you see an integral of two things multiplied by each other and there's like a derivative in there somewhere, you should integrate by parts. Yeah? This is like a life philosophy. I've basically built a career on it. Okay, so, right, so what do I get? Well, I get a boundary integral. I told you we're going to dredge up all those parts of calculus that you don't remember. Yeah? And okay, so what's the boundary integral going to be? Well, it's Vx minus grad f of x, all of that scaled by g of x dot product with the normal dl. Plus, because of the minus, not going to catch me this time.
You used the minus in the first term.
Did I? I did. Yeah. Okay. Fine. It's going to be 0 in a second anyway. Okay. Right. And in effect, if you can't remember Green's theorem, Stokes' theorem, all that good stuff, it's really easy to remember. All you do is you take one of the gradients and you move it to the other side, and then you just choose whatever makes sense, right? So if I want to put a gradient in front of a vector field, what's like the only thing I can do and get a scalar out? Divergence, yeah? And indeed, that's the correct thing to do here. So that's the divergence of this guy. I know it's true because it's giving me the equation I want, but you know, I know that and you don't. Okay? So again, if you can't remember integration by parts, just grab your favorite derivative and move it to the other side and throw in a boundary term, and you're probably okay. I think in this particular case, this is the divergence theorem. If you remember your multivariable calculus class. Yep. Okay, fabulous. And this thing equals, again, 0 for all g. Can't say that enough. Yeah? So in particular, okay, so let's say this is my region omega, and this is where we're going to start drawing pictures and stop doing math for a second, because this is a CS class and we're allowed to. Okay? So this thing has to be true for any g, including g's that are maybe 0 on the boundary and really pointy at just one location. Like hella pointy, right? To the point where it turns into like a Dirac delta function. It just picks out the value of my function at one single place. Yeah? So first of all, if g is 0 on the boundary, this term just goes away. Yeah? And what I'm left with is this thing integrated against an arbitrary g equals 0. So what did this thing better equal? 0, right? In other words, if I have a number and I multiply that number by a bunch of other numbers and I keep getting 0, then that first guy better be 0. Yeah, and that's exactly what's going on here. So in fact, what we just sort of intuited is that the divergence of g is equal to the divergence of the gradient of f in the interior of my domain. Remember that this is just like a function, right? This is like input data, and this is my unknown. Anybody know what this operator is called, the divergence of the gradient? This is called the Laplacian operator. This is going to be our main object of study in the second third of this course. Yeah? So what we showed is that f actually satisfies, sorry, I'm out of space thanks to our board problem here, that the gradient of f is equal to, or the Laplacian of f is equal to the divergence of g, of v rather. And notice this, there's no g in here anymore. Yeah? Really sneaky stuff. Yeah, so this is a way to go from the weak form of a differential equation to the strong form, if these are keywords you've heard before. Okay. Now, let's say that I take a function g and I make it really pointy right on the boundary. Yeah? So now I'm going to start killing these interior terms. These start to go away. And what I'm left with, well, is again the integral of g of x against this thing dot producted with the normal. So what else can I read off? Well, I can read off that v of x dot product with the normal to the boundary is equal to the gradient of f at x dot, oh man, this is ugly, I'm sorry, for all x in the boundary of my domain. Yeah? And this is a very typical pair of equations to come out of a proof like this. I'm so sorry, my handwriting is hard to read because this is really low. Essentially, it's saying this thing equals 0 on the boundary, okay? So what did we just derive? We showed that if f is the minimizer of this thing, this is called the weak form of a problem, then in particular it satisfies two conditions. In the interior, its Laplacian is given by the divergence of v, and on the boundary, the dot product of its gradient with the normal is equal to the dot product of v with the normal, okay? And this thing is called a Poisson equation with a very particular type of boundary condition, right? So you might have heard of Dirichlet conditions and Neumann conditions, all that good stuff. This is something that's sort of Neumann conditions. Typically, I think we think of Neumann as having a 0 there. And essentially, this is one way to derive the other name of the Neumann boundary condition, which is natural boundary condition. Yeah? So if you've ever heard of a natural boundary condition in physics, why is it natural? Well, was there any boundary condition when I wrote this problem down? No, but I found one. Yeah, so it's somehow natural to the problem. Okay, so if this derivation was a little shaky and weird, what were the key pieces? One was taking slices through some functional, saying like, what is my unknown in this problem? It's a function f. That's a complicated object. So instead, I'm going to kind of take directional derivatives in some other direction g. That's piece 1. Piece 2 is integrate by parts. This is almost always true. And then piece 3 is figure out all the different things that have to equal 0 after I did that. Okay? And so on your homework, you're going to follow exactly the same formula to derive a gradient for arc length. I saw a hand back here? Yeah.
Do we require that omega is three-dimensional?
In this case, actually, I was thinking of it as a region on the plane. 3D will work too. Yeah. Yeah.
So is this translating like the optimization problem into like solving a PDE then?
You got it. Yeah. So I took an optimization problem, a variational problem, if you want to impress your friends, and I converted it into a linear system of equations, right? A differential equation. Yeah. There's a hand here. Yeah. Oh, like why isn't the minimum here 0? Sure, yeah. We'll do that really quick because that's going to suggest when we talk about the de Rham cohomology in a few weeks why you need a particular structure. So let's say that I have a vector field which looks like that. Yeah. So in particular on the plane, let's see if I can do it right. That vector field on the plane, right? So what do the traces of that vector field look like? They look like that. Yeah. Well, if I want it to be the gradient of a function, that would mean if I walk in this direction, the values of f would keep decreasing. But eventually I made a circle, yeah? So that clearly can't happen. Right, so this is, there's vector fields which are called exact and co-exact, and I can never remember which one is which, but this is one of those two. Yeah. Yes. Oh boy, you guys are killing me today. This would be like, you're trying to find the electrical potential explained by, what's the gradient of an electrical potential? Electric field, thank you. Yeah.
What if I plug in this into this?
What'll I get? Well, I'll get something which is a, well, there's no v to plug in, that's input data. If I plug in f, I'll take its gradient, it'll be the sort of thing that's closest to v, but is also the gradient of a function. I can't. Oh, in this case, that'll give you 0 actually for f. There's an additional fact hiding here, which we'll cover later, which is that the space of circulating vector fields and the space of potential vector fields are sort of orthogonal. And so that circular vector field is purely circulating. There's no potential piece to it at all. So this will actually give you 0.
Oh.
Yeah. Mm-hmm.
So physically, the circulating thing, like...
It would be kind of like magnetic potential.
Yeah.
Yeah. Absolutely. Yeah, and all of these things have nice explanation in physics, and I'm guessing these people in the back know more about that than I do. Yes?
So we assume that both equals have to evaluate the zeros. Is there a reason we only possibility that
They're equal and opposite. Oh, yeah, I snuck something past you here. Yeah. So remember, this is true for all g. Yeah? So in particular, I said, well, what if I choose a g which is equal to identically 0 on the boundary, and really peaked at a single place, so that effectively this just vanishes. Right? So I think you maybe have the game a little bit confused. The game isn't that there's some g for which this is true. It's any g, so I get to choose the one to evaluate. Yeah, so I choose the one that's best for my purposes. Okay. Okay, so I think I've had enough calculus review. Let's talk about curves. Now let's do some actual geometry today. Okay, so let me flip slide decks here, finally, and back onto comfortable ground. Okay. Oh, I thought you were showing me, there's like curves on the back of your computer there. I thought you were trying to show them to me. Okay, right. So now we're going to talk about things that are unambiguously from the world of differential geometry. And what we're going to do is actually use this as a little bit of a microcosm for the challenges that happen when you take smooth things that you might have seen and try to make them work on a discrete object. Okay, so this is really to our bread and butter. I have the pleasure in this course of teaching a bunch of computer scientists all of differential geometry in half the time. So we're going to have a very high-level picture of what goes on there, followed by really trying to make it concrete on the computational case, because that's the part that matters for us, right? So today, we'll probably mostly do the smooth stuff, and then finally in our next lecture, an algorithm will appear. Yeah? Okay, so first, I've got an extremely philosophical question for you guys. What is a curve? The set of points. Somebody looks at the slide. Yeah. So, right, so a curve is a one-dimensional object, right? So it's a piece of geometry, it's a set of points, right? But actually defining the term curve is a little bit of a tricky matter in geometry world, yeah? I think typically when you take calculus class, we think of a curve as a function from the real numbers into like R2, R3, whatever. Is this thing a curve? We're going to have like the Dr. Seuss approach to geometry today. The answer is no, right? And there are plenty of counter examples. So here's a very simple one, which is phi of t equals 0. Yeah, it's a perfectly valid function. It's differentiable. But I would argue that this object is not a curve geometrically. It's a point. Yeah? And so hopefully you get the point here, which is a little bit pedantic. Yeah. But in fact, actually, you can come up with some really nasty counterexamples that really make you think a little bit about, like, well, what defines a curve geometrically, right? So it's clearly, it's not just a function. And in fact, another way to see that, so here's two different functions, f1 and f2, right? So f1 is t comma 2t, yeah? And the other one is t comma 2t when t is less than 1. And then when t is greater than 1, what happens? Like this little dude in his race car jams on the accelerator and it zooms 2 times as fast. I would argue that these are the same objects geometrically, even though from a calculus perspective, they're quite different. Yeah? So hopefully you get the point here, that a curve really is like the exhaust coming out of the back of the car. It's not the car itself and the path over time. Yeah? There's like a whole zoo of examples of differential geometry. People love to cook up really bizarre counterexamples that look innocent, but then you plot them and bad things happen. Another famous one here is the t squared t cubed curve, which is differentiable as a function in time. But what happens? The car drives up to this point, stops for a second, turns his steering wheel, and then keeps moving, right? And so geometrically, I would say, yes, this is a curve, but is it a smooth curve? No, it's not smooth. It's got a cusp on it. But could you detect that from this function here just by like taking its derivative? No, right? Because this is actually a smooth function of t. So hopefully you guys see that there's some relationship between calculus and geometry, but just be a little careful the way that you go about it. Yeah, that's the main takeaway so far. Okay, so the geometry of a curve, if you really want to know what is a curve is a set of points, just like we suggested. You killed my punchline here. And it's a set of points with certain properties. It isn't a function. It isn't a trace. It might be given by a function, but it doesn't have to be, at least a priori. We'll see that indeed it does. And that's really what matters. Are all sets of points curves? Well, no. So there's obviously some conditions we need beyond that. Yeah. So let's formalize it a little bit. The reason I'm doing this pedantically is now when we talk about manifolds, then we'll just essentially take what used to be the number 1 and stick it in an n, and life is good. Yeah. Okay. So I would argue that the sort of nice geometric definition is that a curve is a set of points that, if I take my magnifying glass, I get close enough to those points, eventually it kind of looks like a line, right? This is the picture we draw in calculus class, and of course that a differentiable curve is one where if I zoom in, it really looks like a line segment and not like a pointy thing. Yeah. Where we'll define pointy thing in a second. Okay? Right, so if you crack open your favorite differential geometry textbook, you look at the definition of a curve, it's quite a mouthful, but it's actually pretty intuitive what's going on. Yeah? So I made my best attempt. I'm sorry, I'm not Keenan. Somebody sent I think you sent a link to Keenan's course notes, and they're absolutely beautiful at Carnegie Mellon. I'm a terrible artist. This is as good as it's going to get in this class. So I encourage you to look there for some nice art and nice math as well. But this is as good as it gets for here, and I think reasonable. Which is, what is a curve? So let's say I'm sitting on the plane. Well, a curve says I grab a point P on this set of points, and I draw a little region around it. I'll call it U. And that the restriction of my set of points to U admits a little function that maps into it, that looks like a curve. Okay? Notice that U has to be sufficiently small. So for instance, let's say that I have a curve like, the letter omega, and here's my point P. If U were too big, and I took the intersection with that, it wouldn't look like a function because there's two things here. But obviously, if I made my neighborhood small enough, then that goes away. Yeah? Okay. I think I've belabored this point enough. But if you look at the definition here, which is, I'm noticing, far too small, you'll see that really that's all it's trying to say, is that a differentiable curve in Rn is a set of points C with the property that for every point P in C, so that's like this blue guy here, there exists a neighborhood U around P and a function gamma so that the intersection between C and U, so that's like this little curve segment, is the image of gamma. And there's one additional condition, which is that the derivative of gamma is non-zero, right? Because I don't want to be in that cusp scenario where my car gets to stop and then turn its steering wheel and keep going. Okay? So that's all this definition is saying. That make sense to everybody? Unfortunately, actually, there's kind of a funny thing that happens in the differential geometry of curves. I would argue that somehow the philosophy we'll cover in the next couple days on curves is exactly opposite of almost everything else we do in differential geometry. Curves are purely extrinsic objects. Like, they're not interesting intrinsically. They're just pieces of string, right? Like the distance function on a curve is just like y equals x, yeah? So, notions like curvature really depend on the space around the curve. They don't depend on the curve itself, which is somehow opposite of when we talk about curvature on a surface. And similarly here, the very first thing that we do when we define a curve is that we define a parametrized curve, which is just a function, which is somehow exactly the point that I don't want to give you guys, right? And the reason for that is that all curves can be written as functions, and that's only because they're one-dimensional objects. This part doesn't extend, right? Like, I encourage you to try and take a triple torus, like 3 donuts glued onto each other, and write that as the image of one function. Right? That's a tricky matter. But for a curve, it's not so bad. Yeah? Okay, so a parametrized curve is basically just a function gamma of t into Rn with the condition that the derivative is always non-zero. In other words, I have a car that's driving along it, right? So t is time, and gamma of t is the position of the car. My car can speed up and slow down, but that's not what I care about. What I care about is the trace of the exhaust pipe, right? Like the stuff that the car actually traces behind. Okay? All right, so there's all of our definitions. A few more vocabulary words that are useful to know. When I talk about the trace of a function, this is the idea that if you give me a function gamma of t, I can get a curve as a set of points, as a sort of image of some interval. Right? We'll call that the trace. And the other thing is that occasionally we'll talk about component functions. Right? So gamma of t is like a point in R3, and if you look at the x, y, and z functions of t, those are the components. Okay. So when we talk about the differential geometry of curves, again, remember that we're completely 100,000% focused on the shape of the stuff that the curve traces, that the car is tracing out as it drives. What's irrelevant is if my driver hits on the accelerator pedal and moves faster or slower along the curve. That does not matter. Okay? And so, in particular, one thing that sort of shows up over and over and over again, and if you take a theoretical differential geometry class, you'll get sick and tired of doing these calculations, which is that if you have some calculation on a curve that depends on the parameter, you've done it wrong. So, in particular, let's say that I have a curve, gamma of t. So I have a parametrized curve, rather, gamma of t. And I cook up a new one. So in particular, I have a function. I'll stop talking for a second and erase. Okay, so I have a parameterized curve gamma of t. And in addition to that, so he goes from A, B, into, I don't know, you want to be 3D or 2D today? Let's be 2D. The board's flat. And in addition to that, I have a function phi, which goes from A, B into R. In fact, actually, just to make our life a little easier, let's say that we go from AB into AB. Maybe it's even bijective, whatever you want. Okay? I can make a new curve. New, yeah, by defining the following, which is gamma squiggle of t which is gamma of phi of t. Yeah? So what did I do? Did I mess with the shape of the curve? No, I just messed with the speed at which I traversed the curve. Right? I just warped the time function by sticking in a phi. If I do a calculation on my curve and a factor of like d phi pops out, would that be considered valid or useful or interesting in differential geometry? No. Right? Because that doesn't have to do with the shape of the curve. That has to do with how reckless my driver was as he drove along the curve. Does that make sense? So let's do an example. So let's say that I want to compute velocity. Yeah? I want to compute gamma of t. And maybe I think like, oh, so here's my curve. I'm going to associate it to a tangent vector. We'll call it v. And that's the velocity of the car as it drives. So what is v of t? So maybe what's v tilde of t? Well, it's like gamma prime by the chain rule. Yeah? Notice this thing came out, right? So the same point could be associated with two different velocities. So this is a function of the curve? No, it's a function of my parameterization. Hopefully we get the point there, right? Right. So in other words, velocity is not a valid differential geometric measurement on a curve. It's not a measurement. It's not a thing I can do with a ruler. I have to know the path of the car as a function of time. Okay? What is an example of something I can measure? Length. Fabulous. So hopefully you guys remember from calculus class, the length of a curve, yeah, is the integral of the derivative, the norm of the derivative, rather. Yeah? And so for fun, we have about 10 minutes left here. I think we can do this calculation. Let's double check that this thing actually is invariant to parameterization. By the way, that phrase you'll get sick and tired of writing down if you do lots of geometry research, right? Because everything you do is like, maybe I'll say, okay, I'm going to propose this number as an invariant of a curve. The very first calculation I have to do is to say, suppose I had some other gamma that traced out the same curve, make sure I get the same number, right? Because if I didn't, then this was verschlicht. I shouldn't have done it to begin with, yeah? So let's do an example of this calculation. We're not going to do too many because I'm bored of them. But we should do at least one for moral purpose. Okay. So let's say that I have another parameterization in my curve. I'm going to write it as gamma tilde of t equals gamma of phi of t, right? And I'm going to say that, in general, I'm going to define the length of a curve. Notice this funny notation again, right? It's like a function that takes in a curve, outputs a number. Which goes from a curve to its length from between A and B. Okay? Okay. By the way, we're going to have to be a little bit careful with these A's and B's are going to change if phi remaps the interval. Yeah, but we're all grown-ups here, so I think that should be okay. All right. So let's say that I want to compute the length of phi squiggle, or gamma squiggle here. Well, what is the derivative of this thing? Well, it's really gamma prime of phi of t, phi prime of t. Everybody see that? That's from the chain rule. Nods? Signs of life? Anything? Like look up? There we go. Okay. Okay. Remember, this thing is a scalar. This is a vector, right? So I can take this guy out of the norm. That's okay. Yeah. So this is the absolute value. Okay. And I'm going to make a quick assumption about my function phi because I'm lazy, which is that it's got a positive derivative. In other words, it doesn't flip the orientation of the curve, in which case I'd have to worry about sign. Okay. So if I do that, then I can kill these absolute values. Okay? And I'll let you guys double check the other case at home. Okay. What is this thing screaming out to do? I have a phi prime times dt. Change the variables, yeah? In fact, one thing I'm going to do is, just to be consistent, let's make a bunch of t tildes like that. Okay? And let's define t to be this thing, right? Like that, okay? Well, then by the change of variables formula, what does my integral end up being? So remember that dt equals now phi prime dt tilde, yeah? So in other words, this is the integral from a to b, the norm of gamma prime of t, where a and b are chosen to be the right values. Okay? And of course, this thing is the length of gamma. Yep. So what did we just prove? We just showed that this particular thing, the way that I defined it was a thing that takes in functions and outputs a number. But secretly, it's an object that takes out in a curve and outputs a number. Right? And the way that I double checked that is I said, well, suppose I have another function gamma prime which traces out the same curve, then I got the same number, right? So even though I've, just for convenience of notation, I've written it this way, and I'm using the language of calculus to do that, that's really irrelevant. Do you see that? And that's the type of calculation we do quite a bit of in the differential geometry world. Now, there's something that's a little bit of a headache here, right? Which is like, okay, so every time I do any calculation at all, now I'm going to have to double check this invariance to parameter, right? That for any of these functions phi, I could choose phi, my calculation didn't change, and hence my measurement was an okay thing to do. And that seems like kind of a headache, yeah? And in particular, we're going to define things like curvature, like the bendiness of my curve up next. And it's just going to be no fun at all if I have to like keep doing all these nasty calculations. And so there's a dirty trick that people do in this area of math, which is to define a useful parameterization and say, as long as I write things in terms of just this parameterization, I'm okay. Does anybody know what that thing is called? Arc length. Yeah, unsurprisingly. We only got one object to work with. Yep. So I've purposefully been trying to give you guys a little bit of intuition for what's going on. In terms of, like, let's say that I'm a car and I'm driving along my piece of string. Yeah? And you know, as I'm driving along my piece of string, there's a lot of things that I can measure, right? I can drop a piece of measuring tape behind the car and measure how much stuff has gone along, right? That's like what I've done here. If I'm the driver, I also feel different forces as I drive along, yeah? And what are the different forces I can feel? Well, even if my curve is a straight line, you know, like for instance, if Magnus is driving, you know, he jams on the accelerator and I feel a force into the car as it kicks off, right? Is that an interesting geometric signal? No, that's a signal about Magnus, yeah? So instead, what do? Well, I have a boring driver like Sebastian who likes to go, actually I've seen him ski. Let's say that I'm driving, so I drive at a nice constant unit speed. Can I still feel force? No, you're being too agreeable. The answer is yes, you still feel force. So let's say that I'm driving over a hill, yeah? There's force that is intrinsic to the fact that there was a hill in front of my car. And then there's force that happened because, you know, Magnus is sitting next to me and he reached over and hit the accelerator. And those are two different types of forces. One of them has to do with geometry, and one of them has to do with my driving. So how could I just sense the interesting geometric one? Well, I just drive with constant speed. Yeah, I don't speed up. And that's called parameterization by arc length. Yeah? The idea that if I'm just driving by constant speed and I still can measure something interesting, then that must have had something to do with the curve. In our next lecture, we're going to take that and we're going to decompose it into two pieces. One piece has to do with turning the steering wheel, and the other has to do with driving over a hill, right? And one of those is curvature, and one of those is torsion. But for now, let's quickly define parameterization by arc length and then call it a day. Okay? So in particular, let's say that I have a curve, gamma of t. And gamma could be any darn thing, right? It could be, you know, Magnus is messing with the accelerator all kinds of different ways. He's speeding up and slowing down. He's a very erratic driver. And I'd like to kind of get rid of that behavior, which is true. So one thing I could do is define a function s of t, which is the length of the curve from some fixed time t naught to the current time t. Right? So at time t naught, this is 0. Yeah, and it's kind of like my car, you know, I attached a piece of string behind my car and now I'm letting it like unravel as I drive, and I'm just looking at the number of inches that have passed by, right? And that's the function s of t. Everybody get this thing? If I invert it, then I get a function t of s. Kind of reasonable? Yep. So I'm going to define a new parameterization of my same curve, gamma tilde of s here, to be gamma of phi, where phi is defined to be the inverse. So in other words, the thing that goes from time to, from arc length to time. Okay, so why do I do that? Well, let's quickly take a derivative. Next class, I'm going to figure out this projector scenario so that I have more boards to work with, but I think I can work in this little square here. Okay, so what is d gamma, I guess gamma tilde, fine, ds? Well, in some sense, it's, well, in the mathematical sense, it's d gamma dt dt ds. Yeah? Okay, what is dt ds? Well, for one thing, it's 1 over ds dt. Yeah? This is technically the inverse function theorem, or it's like a Leibniz notation finally working the way it should. Yeah? So this is d gamma ds divided by ds dt. Obviously, I'm being quite sloppy about math. The actual proof is in the lecture notes, and I'll let you look closely here. Okay, what is ds dt? Remember that s is equal to the integral of this integrand, right? The norm of gamma prime. What happens when I differentiate an integral? Ah, come on, guys. I only ask easy questions. Yeah, if I have the integral and then I differentiate it again, I just get the thing on the inside. Yeah? Right? This is the fundamental theorem of calculus. It's kind of a big deal. Okay, so in particular, what is the integrand in this case? Well, it's d gamma ds divided by the norm of d gamma, oh shoot, that should be a t. Sorry, see, there's a t there, I just copied wrong. What have I done? Like that. That makes sense? What happens when I take a vector and I divide it by its length? I get a unit vector, right? So do you guys see what I just did to this curve? I made it boring from a driving perspective, right? By reparameterizing, like warping time, essentially I canceled out the effect of Magnus's dangerous driving, and what was left over was a boring constant speed driver along the curve. Yeah? And here's the thing. Anything that I measure in terms of gamma tilde of s, like if I take derivatives of this function, I can associate that to the geometry of my curve, because there's only one way to drive along my curve with unit speed. That sentence is debatable. I saw some eyebrows go up. Why is that? What did I just forget? There's actually two ways to do it, right? One is like I just turn my car around, I drive the other way. Yeah. So there's still one thing you have to check, which is that like if I flip my car backward, I get the same expression. Okay, so maybe we'll stop with that for now. So the next question that we're going to ask you guys is, okay, so what kind of geometry can I measure for my curve? Right? Like what does it mean to measure the bendiness of an object? And so we'll do that real quick in our next lecture, and then we'll figure out how to discretize it. And what we'll show, unfortunately, is that you can't. There's a bunch of different notions of curvature that all agree in the smooth case and all disagree in the discrete case, which is kind of a downer. Okay, so with that, I will see you guys on Tuesday. Don't forget your homework and your reading assignments and your projects, all this kind of stuff going on at the same time. Hopefully I haven't scared you away yet. Yeah, we'll see you soon.